Hello and welcome to the lecture CNN Model Architecture Part 2. In this lecture, we mainly focus three important CNN based network, namely Densenet, Mobilenet and Efficientnet. So we start with Densenet. The full form of Densenet is densely connected convolution network, which is a convolution neural network architecture that introduce direct connections between every layer and all subsequent layers within a dense block. What actually it means? So here you can see the initial architecture of Densenet. Now initially when we have studied convolution neural network, then there is only these connections. But in Densenet, you can see that this is connected to this is also connected to this is also connected to this layer, and this also this. So every subsequent layer or successive layers from input to the output are connected, and that is the basic idea. So it's a convolution neural network architecture that means a direct connection between every layer and all subsequent layers within a dense block. So within a dense block, this is basically the architecture. That is the way a dense net or densely connected convolution network is separated or is separate from a conventional CNN. Now what we say, unlike traditional CNN where each layer receives input only from the previous layer, here in Densenet concatenates the feature maps from all preceding layers. You can see if you take this layer, what are this is from last layer, this is from last to last layer. If we say this, it is from this layer, the last layer, last to last layer, last to last layer, again the first. So all the previous layers is connected to this. So that's why they say Densenet concatenates the feature maps from all preceding layers and uses the input for the current layer. Right? This dense connectivity, that this is the connection is very dense, improves feature reuse. Definitely that since it is connected to those, strengthens the gradient flow and alleviates the vanishing gradient problem, enabling the training of very deep networks with fewer parameters. So major improvement what we can get, definitely it improves the feature use. It is very densely connected. Then strengthen the gradient flow because there is a multiple pathway to the back propagation as we have seen in the ResNet in the last class, and alleviates the vanishing gradient problems due to this back propagation, that's multiple channel of back propagation, enabling the training of very deep networks with fewer parameters. So this is the basic definition, a very naive definition of the we have taken this is a 5-layer dense leg block with growth rate k is equal to 4. Each layer takes all preceding feature maps as input. Now you can see this is taken from the main paper, which is basically 2017 CBPI paper of Gao Huang et al. So this is the very basic definition of the dense net. Now this dense network architecture typically consists of an initial convolution layer that you can see here, initial convolution layers, these are all convolution layers, multiple dense blocks separated by some transition layers like this is a transition layer and a final classification layer. Okay, so this is that the multiple dense blocks are separated by a transition layer like this and a final classification. Each dense block contains several convolution layers, while transition layers include batch normalization. You can see here B, Bn, and a 1 by n convolution, that is basically a bottleneck kind of thing, and average pooling to reduce the number of feature maps and spatial dimension. So there is some poolings. So this is basically the kind of transition layer. Okay. Now, by encouraging the feature propagation and minimizing the redundant learning, that Densenet achieves a high classification accuracy. So definitely feature propagation from multiple previous layer, and minimizing the redundant learning that which is basically try to alleviate, which is common. We have to minimize the redundancy. Densenet achieve high classification accuracy with improved computational efficiency, making the well suited for image classification, object detection methods. So this is the Densenet. When comparing Densenet with conventional CNN, that we can have this if we have a L layer CNN. The L layers typically contains L direct connection. For example, in this particular, there is a 6 layers, hidden layers. You can find 1, 2, 3, 4, 5, and 6. So 6 connections within this layer. This is for classification. So this is a 6 connection. So L direct connection. So this is it. Okay, where each layer receives input only from the immediately preceding layer. So this is coming from here, this coming from here, coming from here, this is from here, and so on. Preceding layer and passes it output to the next. Okay. So this is the very simple. For example, a traditional 6-layer CML, a 6 sequential connection. That's what we have seen, represented by the straight arrows between adjacent layers. In ResNet, there is some additional this kind of skip connection. This is somewhat useless. But in our Densenet, you can see this. In contrast, a Densenet introduce dense connectivity. So total how many? It is L into L plus 1 by 2. That is 6. L is equal to 6 here. 6 into 6 plus 1 by 2, 20. Now how can we get? From here, that is 1. From this, 2, 3, 4, 5, 6. So 6 to 6. So from here 5, from here 4, from here 3 and 1. So if we add all this 21. So it is the formula 20. So Densenet introduces dense connectivity where each layer receives feature maps from all preceding layers and forwards its own feature maps to all subsequent layers. And as a result, L layer Densenet have what we have said before, L into L plus 1 by 2 direct connections. Okay. So therefore, for a network with 6 layers, the total number of connection is 21. So this is the main idea. This dense connectivity promotes the feature reuse, strengthens the gradient propagation, alleviates the vanishing gradient problem, and improves the parameter efficiency as we discussed before by allowing the later layers to access feature learned throughout the network. So as a whole, this is a very brief idea about Densenet, and it's become very important. Next, we start the Mobilenet. So Mobilenet is a lightweight convolution neural network that basically designed for efficient image classification and computation tasks on resource-constrained devices, such as smartphones, enabled these embedded systems, and IoT devices, etc. So, what is the basic idea here? That this Densenet, even this ResNet, is a very resource hungry or kind of the deeper network. Now, it is not that much suitable for mobile phones or embedded systems because these are resource constrained ones. So that much resource or GPU hardware is not available there. So for that reason, this mobile net important. So what is the basic idea of mobile net? Is they introduce a very interesting concept. It's called depthwise separable convolution. This is a factorized convolution technique that significantly reduces the computational complexity and model size compared to the standard convolutions. Now here the idea is basically that here the basic idea to reduce the computational complexity so that it becomes ready for this kind of handheld device or research conference device like smartphone and touch system. Now, instead of performing spatial filtering and channel combination in a single operation, Mobilenet decomposes the standard convolution into two sequential layers. One is depthwise convolution, other is followed by pointwise convolution. Okay, so these two things that first of all, the first they are doing depthwise convolution followed by pointwise convolution. That we have to understand what this means. This factorization significantly reduces the number of parameters and floating point operation that drops while maintaining the competitive accuracy. And that is the very basic idea of Mobilenet. Okay. Now, what do you mean by depthwise separable convolution? Depthwise separable convolution is a form of factorized convolutions which factorize a standard convolution into depthwise convolution and one-to-one convolution called pointwise convolution that will be defined in subsequent slides. The depthwise convolution applies a single convolution filter independently to each input channel, enabling efficient spatial feature extraction without mixing channel information. So that we'll see later what actually it means. That what depthwise convolution is basically convolves the using these images or the inputs in the each different input channel separately. Okay, single convolution for independently to each channel, and then we put a pointwise convolution. So subsequently, the pointwise then implemented one-to-one convolution combines the output across the whole channels to generate a new set of channel maps. So these two things, what it has been proposed in case of Mobilenet. Now, if we try to discuss that what is depthwise convolution? Depthwise convolution is a convolution operation in which a single convolution filter is applied independently to each channel of a feature map. Okay, unlike a standard convolution which is simultaneously perform spatial filtering as combines the information across all input channels, depthwise convolution process each channel separately without interchannel mixing. Now, you please see here. This is the image mn into k. So m is height, width, and its number of channels. Now, depthwise convolution means this is a k number of filters, and every filter is p by q, and this is 1. Okay, so this is the basically the idea that this channel is this is a single dimension. So this channel is single. So it's a p by q. It's another p by q, and how many numbers? So input, if the input has a k channels, this is a k channel. Depthwise convolution employs k distinct filters. Okay, each operating on one corresponding channel to extract the spatial features. So every channel, you can say there is a k different channels. If you say if we just bisect in k channels, so we have a k kind of image here. For first image, this filter is used. Second image, this filter used. Third and kth image, this filter used in the two. Okay, so this operation significantly reduces the number of parameters and computational cost, because it eliminates the need to convolve across all input channels, definitely. So that will, and we get this R into S because of this P of Q, these things. We have some convolution is there based on the stripe, this R in S and this in H. So this is the output. Okay. Now come depthwise. A single convolution operation means P into Q multiplication. So since filters is slided into R by S times across all K channels, the total number of multiplication become K into, because K is a number, into RS, this RS and P and Q. So this is total number. So this is the depthwise convolution. This number of convolutions. Now come what is the pointwise convolution. However, this depthwise convolution doesn't combine the information between channels because each channel is separately treated. So it is typically followed by a pointwise convolution, one by one convolution, which integrates the channel-wise feature into a new set of outputs. Now you can see, now this is one filter. This is only one pixel, but for all K channels. So it is, so this, there's how many? It's L, the output feature. So the pointwise convolution, total number of multiplication into K is because this number of K is there, into M into N. So that means into, and this kind of into L, that because these two things are same. So this is the pointwise convolution. Now for depthwise convolution, so for depthwise separable convolution operation, total number of multiplication is K into R plus R into S, P into Q plus L. So this becomes. But if you know the standard convolution, it is L into R into S plus P into Q into K. So PQ plus L into this K into RS. But here K into RS into PQ into L. So if P is equal to 512, P is equal to Q is 512 and L is 100, depthwise separable convolution 100 times. Okay, and that's why it's much faster. Okay, so this is the depthwise separable convolution. So as a whole, if we summarize it, Mobilenet, a standard convolution, simultaneously performs both spatial filtering and channel-wise feature aggregation in single operation, resulting substantially higher computation cost. Okay, so what we understand, the standard convolution is associated with high computational costs. So by separating this process, depthwise separable convolution substantially reduces the number of parameters and these flops while preserving the strong feature representation. The computational efficiency that we have just shown. This computational efficiency makes the Mobilenet particularly well suited for deployment of resource consuming devices such as smartphone, embedded system, Internet of Things application, by low latency or limited memory critical. Also, we understand because their computational efficiency is a matter of this kind of low latency limited memory devices where resource constant device. So if the number of computation is less, most subsequent versions including Mobilenet V2, we further enhance the performance through innovations such as inverted residual blocks, linear bottleneck squeeze and execution modules and neural architecture. So these are some advanced proposals where that make this Mobilenet V2, V3 more improved over this Mobilenet V1, what we have discussed. This making the Mobilenet family well suited for real-time application requiring high accuracy with low latency and minimal memory consumption. So this is the basic idea, very good. So in this course, we have a very limited scope to discuss. So this is important. Now we discuss the Efficientnet. Now Efficientnet is a family of convolution neural network that achieves a high classification accuracy with significantly fewer parameters and lower computational costs through a compound scale strategy. That is the efficient. It is use the significantly fewer parameters as well as it's maintain the lower computational cost, and in that sense it is efficient. So unlike conventional approaches, there's arbitrarily scale network through depth, width, or input image resolution independently. Efficientnet uniformly scales all three dimensions using a fixed set of scale. The idea is that some work in the previous discussion, what we have seen, that we increase the depth. Some network or some proposal within this timeline that we propose that width is also. So there should be some balance between depth and width. Another thing is input image resolution. That if input resolution is high, then efficiency is high. So these three parameters, they are worked with, but they're worked with independent. But efficient with the some uniformity it imposes among the scales of all three dimensions using some fixed set of scale. That is basically the idea of efficient. Okay. So their base model is efficient visual, is designed through a neural architecture such as employs mobile inverted convolution blocks, which incorporates the depthwise separable convolution that we discussed in case of this Mobilenet, inverted residual connection, linear bottlenecks, and skews to its extension models such and such to enhance the feature representation while maintaining the computation. So this is the major innovation that this base model of Efficientnet has been achieved or has been proposed. Now, the higher variants of this, B1 to B7, are generated by systematically applying the compound scale, so resulting in the improved efficiency without a proportional increase in computational complexity. First of all, this what we mean by compound scale, that we'll see our subsequent slides. The architecture also utilizes batch normalization, the Swiss activation function, and the residual connection, facilitate the efficient gradient propagation and stable training. So these are the innovation that made in this. When to its balanced scaling strategy and optimization building blocks, Efficientnet provides an excellent trade-off between accuracy, model size, and inference speed, making it well suited for image classification, object detection, transfer learning application, and so on. Particularly in environments with limited computations. So this is the basic definition. Now, what do we mean by model scale? Now, normal CNN can be scaled to just satisfy different computational and memory constraints by increasing the network depth, network width, and input distribution that we have understood. For example, ResNet family scales model capacity by varying the number of layers, while architectures such as wide ResNet, BileNet increase the representation by expanding the number of channels. So width or channel. Similarly, increasing the input image resolution enables the network to capture finer spatial details because resolution, often leading to improved classification at the expense of higher computation and increased flops, floating point. So that we have seen our previous examples, or previous model examples. Now, although the previous studies have demonstrated that network depth with significant influence the representation capacity and learning ability of CNN, this dimension have traditionally been scaled independently. That is very important. There are no balancing trade-off, resulting in suboptimal trade-offs between accuracy and computational efficiency. Exactly here, the Efficientnet address this limitation. Exactly this limitation by introducing a compound scaling strategy that systematically and uniformly scales network depth, width, and input resolution using a fixed set of scale. There we see. This balanced scaling approach enables the network to utilize computational resource more effectively, achieving superior accuracy while in a relatively small model size and lower computational cost as compared to the conventional scaling methods. That is basically claimed. How they do this? So this is basically the baseline model. This is a normal model. Now, if we say first width scaling, so you can say that the wider that width is high, so we make the wider. Now deeper, so is concept number of layers is high, is the department. And high resolution, resolution. So high resolution images there. So these are the different technique to improve the this performance. But independent of this width, depth, and resolution. While compound scaling is basically deeper, wider, and higher, it's basically have some kind of balance. What kind of balance? That in compound scale the model, the scaling strategy introduces Efficientnet that uniformly scales the three fundamental dimension in a segment: depth, width, and input using a single compound coefficient. So unlike conventional scaling that increases only one dimension at a time, compound scaling maintains a balanced relationship among all these. To maximize the model accuracy, minimize the compression cost. How to do that? They use some scaling coefficient phi, that network depth with input resolution as scaled into the equation d of alpha into phi, w is equal to beta gamma into phi. Alpha beta gamma to define scaling constant into the optimization. So this is basically these coefficients satisfy the constant alpha dot beta square into gamma square is equal to approximately 2. Ensuring that the computational complexity measured in floating point proofs approximately doubles with each increment of the component. This is the kind of balancing. Okay. So by jointly scaling these dimensions in a sensible manner, the compound scaling achieves a more effective balance between feature representation, model capacity, and compound steps. That's what we have just discussed. An independent scaling. Now, this methodology enables this new Efficientnet family V0 to V7 to deliver state-of-art accuracy while maintaining significantly fewer parameters and lower compression. That's what we have discussed earlier. Again, highly suitable for high performance and business compression applications. That is the concept. So, in this lecture, we will discuss three main architecture: Densenet, Mobilenet, and Efficientnet. The next lecture, we start sequential time. First, the RNN.